All right, now again, using technology is the most convenient way to find that equation, but it's also able to do it kind of, doing your own calculations with some means and standard deviations of our two variables and the correlation that we see. So how would we do it? Well, okay, we have the explanatory variable x and response variable y for n individuals. All right, so we have to find the mean of x and the mean of y, and then each of their standard deviations, and then their correlation R. Now, if you do that, you can come up with this least squares regression line. You can find the slope by taking the correlation coefficient times, and then divide the standard deviation of y divided by x. That gives you the slope. And then to find the y-intercept, what you could do is take the average of the mean y and subtract the slope times the mean x. So kind of crazy kooky, but it actually kind of works when you do it like that way. I mean, technology is obviously easier, but those are some formulas you could use if you wanted to do it by hand. All right, so again, as we kind of look here at this picture, we have some different things drawn as far as foot length to height, and then we assume there's a pretty strong correlation between that. The scatter plot shows that, again, it's the regression equation that we have here, and we've added 4 more lines to the graph. We had a vertical line at the mean foot length, which of x, of course, a little over 24, getting close to 25, a vertical line at x plus the standard deviation. Okay, so that's that line right here. And then we did a horizontal line at the mean y height. Okay, so there it is right there. And then we have, of course, horizontal line at y plus the standard deviation of y. That's right here. And then, of course, we have our regression equation going through there. So we have all those different lines added onto there. And so what we're seeing is that for an increase of 1 standard deviation in the value of the explanatory variable, the least squares regression line predicts an increase of r, actually, standard deviations in the response variable y. So kind of works kind of slick there. All right, now this is called regression to the mean because the values of y regress to their mean is what happens there. All right, let's talk about correlation and regression with some wisdom here, and again, some powerful tools when we're describing the two variables, okay? Now, you got to be careful of some limitations. Now, once again, correlation and regression lines only describe linear relationship. Okay, so keep that in mind. So you got to kind of look at the graphs that you have. So it might be appropriate, might not be. And I mean, you can get the same correlation and regression line, but it may not be appropriate. So you got to be a little careful with that. Again, some other things that we have here is that correlation and least squares regression lines, they're not resistant. Okay, so there's some values that can really influence those. And points with what we call a high leverage in regression have much larger or much smaller x values than the other points in the data. An outlier, we kind of know what those are, it doesn't follow the pattern. And then we have an influential point that if we remove it, it really changes the slope, the y-intercept, the correlation, r squared, the coefficient of determination, or the standard deviation of those residuals. So let's kind of take a look at what we're talking about here. The point for child 18, right here, we say it has high leverage because its x value is much larger than the others. Okay, now again, you can see it's still fitting that line. It's still pretty close. The residual isn't that much, but has what we call high leverage. Whereas child 19, you can see here, is an outlier because it doesn't fall within the pattern. You can kind of see if you do this based on the residuals, child 18 doesn't have a very big residual. Child 19 does. Okay, and that's making the difference between that and an outlier. So if we remove child 18, if we looked at that, you can kind of see that it makes the slope, it does make it closer to 0. It makes the y-intercept smaller. It slightly increases the standard deviation, and it greatly, sorry about the misspelling there, decreases r squared. Okay, it really does decrease that, that point. So you can kind of see what happens there. Now, if we remove the outlier, child 19, it doesn't really change the slope or the y-intercept that much. It does greatly decreases the standard deviation of the residuals. And that makes sense because then your data values aren't more spread out. And it does actually increase r squared. So it does kind of make sure that that the percentage of the variability contributed to the least squares regression line now without that outlier now increases that percentage, because obviously that outlier isn't in fact impacting it quite as much. All right, now another thing that we always talk about with correlation regression is that just there could be a great strong association. Doesn't mean that one causes the other. And again, we always want to show that. We always want to show that if we can, but you got to be real careful, okay? Just because there's a strong association does not mean that one does necessarily cause-effect relationship on those two. All right, so look at all the different things we've learned. We've had 4 different sections here. Again, make predictions using regression lines. Okay, keeping in mind the dangers. We should be able to calculate, interpret a residual, get the slope and y-intercept of a regression line, interpret that, determine the equation of a least squares regression line using technology. We should be able to construct and interpret residual plots and see whether or not that regression model is appropriate. We shouldn't see any patterns. Interpret the standard deviation S and the residuals R squared. Remember, that's that coefficient of determination. Be able to interpret that. We should be able to get that from our technology and use those values to assess how well the line models the relationship. Describe how that least squares regression line, standard deviation, and R squared are influenced by different unusual points, as we just talked about, and then find the slope and y-intercept of least squares regression line from the means and standard deviation. So we should be able to compute those from the data that we have. Again, finding the mean of x and y and their standard deviations, we should be able to, and the correlation, should be able to then find the equation of that least squares regression line. All right, so a lot to do in this section, so we'll kind of wrap that up. And until next time, I am Mr. Bone.